All right, you got any questions or need anything before we get started? All right. Excuse me. All right. Today we're going to keep talking a bit about wave stuff. I want to talk about the basic stuff that applies to all kinds of waves, and then later next week we'll talk about some specifics of sound waves, maybe a little about light if we've got time. But reminder, next Monday we're specifically going to take a pause on waves to talk about the eclipse, gravity, and orbit. I'm very excited. Make sure that you grab some eclipse glasses if you haven't already and you want to view the eclipse. I've given all my lectures at least one attempt for people to grab one pair. So if you want a second pair for a loved one or associate, you're welcome to grab one. And then if there's any extras left on Monday, it'll just be open season. But make sure to grab one if you want to watch the eclipse Monday afternoon. You should not do so with your eyes or even sunglasses. Anything in your minds before we begin today? In that case, let's pick up where we left off. Why does my formatting get messed up every time I load this thing? All right. On Wednesday, we talked about waves, how they are traveling vibrations, therefore made of traveling energy. Vibrations can be measured by their amplitude, frequency, and period of oscillation. That means you can measure waves by those things too. But since waves travel, you can also measure them based on their wavelength. That is the distance that they travel in a single wave oscillation. It's also could be thought of as just the literal physical length of one complete wave cycle. But since they're traveling, they also have a speed, a velocity. Even though velocity is the better word, wave speed just sounds better, and so that tends to be what I end up saying most of the time. And it's literally the same velocity as we've always been using. However, there's a different formula that can be used, bless you, to calculate wave speed based on some of these wave variables. That formula being wave speed equals wave frequency times wavelength. And this is secretly the same as the normal velocity formula. It uses the same principles and it tells you the same information. Since frequency is events per second, and since wavelength is wavelength meters, 1/seconds times meters is meters per second. It's the same as the distance formula, it's just a little more specific. Sorry, it's the same as the velocity formula. It just uses wave-specific jargon. And we'll pick up today, we're practicing and addressing all of those concepts before we move on and talk a little bit more about some of the finer points of wave speed. Any objections before a little practice? All right. Here we have a waveform. The distance from the absolute bottom of this waveform up to the absolute top is 8.26 centimeters, and it is a distance of 5.2 centimeters horizontally traveled from this crest to this trough. And since you can't really show this one on picture, I'm just straight out telling you that the frequency of this wave is 18 hertz. With all that information given, what should the amplitude of this wave be? Very good. Wait, say it again.
Well, first it was 8.6,
8.26. You're almost there. Amplitude is defined as the distance from baseline to either extreme. So So what should you do to that 8.26? Yeah, cut it in half. So I would say that the amplitude here would be closer to 4.1, thank you, 13 centimeters. Sound all right? Okay. Next, what would the wavelength be given this information?
36.
It's more related to the 5.2 than it is to the 8.26.
Is it
10.4, very good.
There's two.
Yes, so this distance is literally only half of a complete wave cycle. This is the distance traveled as the wave cycles from a peak, from a crest down to a trough. But to complete a full wave cycle, you'd have to go from crest down to trough and back up to crest. One complete cycle. And since this is only half the cycle, it's only half the wavelength.
Bless you. Thank you.
So that would make the wavelength 10.4 centimeters. Again, physical length of one whole wave, make sure you're examining one whole wave somehow. You could go either crest to crest, trough to trough, falling middle point to falling middle point, as long as it's the next iteration of that point. Sound okay? All right. Next, the information given, what would this wave's period of oscillation be? Not quite. Period is a measurement of time, and what we know about this wave is that 18 hertz means 18 waves cycle every 1 second. So what should you do with that information if you instead want period of oscillation? Yes, you guys are right. Period is the inverse of frequency. They tell you opposite things. Frequency is events per second. Period is seconds per event. So if you have one, just flip it to get the other. So therefore frequency is 1 over period, and period is 1 over frequency. So 1 over 18 hertz would be 1 over 18 hertz. 1 over 18 hertz is 1 over 18 seconds. Since 1 hertz is 1 over seconds, therefore converting it, you get seconds back. And then that number would be tiny, 0.04 or something like that. .05, 555. And again, the larger the frequency, the smaller the period of oscillation. Big frequency means a lot of events happen in a short amount of time. Therefore, it's a small time measurement for a single event to happen. Does that one sound okay? All right, last up, given all the information on the board, how would we find the speed of this wave?
Would be the 10.4 times 4.13.
Almost. It's frequency times wavelength.
10.4 times 18.
Yes, 10.4 times 18. The hertz is the frequency.
So what if you were to, like, if I still were to multiply it like at 0.056, that would be wrong?
You could get the correct answer using the 0.056, but that version of the formula would look like this. Since frequency and period are inverses, you could rewrite the formula like this. And you get the same answer, and I'll try to show that. The frequency was 18, the wavelength is 10.4 centimeters. I'm actually going to convert that to meters for accuracy. privacy's sake. And I'll do the same calculation using the period instead, but that would go underneath instead of on top. And either way you do this, you should get, hold please. .872 meters per second. Does that make sense? So you can get there with the time period of oscillation.
That 0.104, you just moved the decimal?
Yes, this is the same as the 10.4 centimeters. I just changed it so that the unit was meters per second. You could keep it like this, but then you get 187 centimeters per second, which is fine as long as you write centimeters. How do you feel? All right. Now, while we're talking about wave speed, there's a couple of quirks related to wave speed that I want to make sure to cover, because wave speed ends up being fairly important to how humans perceive waves. There being two primary waves that human senses tend to pick up on, sound and light. We use this formula to calculate wave speed, but I wouldn't say that this formula determines wave speed. The speed of a wave is determined by what type of wave it is and what medium it is traveling through, more so than specifically just its frequency or its wavelength. If you take a wave and you increase its frequency, that's not going to make it faster unless you also change the wave type or the wave medium along with it. Sound, for instance. If you have a speaker that's playing 500 hertz sound and you increase that frequency to 1,000, wait, I forgot what numbers I said. If you have a speaker that's playing 500 hertz sound, which is a very low tone, and you double that to 1,000 hertz, that does not mean that the sound is actually going to reach you twice as fast. Increasing the frequency, doubling the frequency wouldn't double travel speed. It would cut wavelength in half, because the speed remains constant as long as it's the same wave type traveling through the same medium. To try to demonstrate, I'm going to use the same spring I did the other day, but rather than try and fail to attach it to my sink, could I get someone to hold the other end of this so that it doesn't accidentally let go of whatever it's attached to? Yeah. Appreciate it, thank you. I just want you to hold on to that end regardless of whatever I do to the other side. All you have to do is not move. So, here we have the medium that a wave is going to travel through. So the medium is spring, wave type is just going to be a single vibration through this spring. And no matter how hard I pluck this thing, or how many times I pluck it, the wave speed doesn't change. Frequency doesn't actually change the rate at which the energy gets to the other side. The waves might get bigger, and you might see more of them, but that doesn't necessarily mean that they are faster. I'm going to show again with a single pulse. And then a bigger pulse. It might shake more, but it's not getting to the other end any quicker. Does that make sense? The only way to change the speed of a wave is to change the medium. And with a spring, you can actually adjust the medium by just physically making the coils tighter. So, again, you don't change anything. You're doing great. So I've made the coils tighter. That has changed the properties of the medium, and now that has changed wave speed. You can see it, right? I'll even strum it the other way. Wave speed doesn't change with frequency. It'd be more accurate to say that by changing wave speed, you're going to change, thank you very much, you're going to change the various frequency and wavelength pairings that multiply together to create that speed. Speed of a given wave type in a given medium is constant, and there are a couple of those constants that tend to come up time and time again. That. On planet Earth, we usually consider the speed of sound to be 340 meters per second through air, as long as that air is of standard Earth surface temperature and the humidity isn't doing anything crazy. You can change that number by increasing the temperature. Hotter air actually transmits sound faster than colder air. You can also mess with the humidity, and that'll change the speed of sound too. But if you really want to make sound faster, what you do is you play it through water. Again, you change wave type or wave medium to adjust the speed. The speed of sound underwater is like 5 times faster than it is through air. And then it's even faster through solid rock, which is why earthquakes are so dangerous. Waves transmit very quickly through stone. But as long as it's air, we consider this to be roughly constant as long as you're not doing anything crazy with temperature or humidity. Different type of wave, that being light, travels several hundred billion times faster. That's 3 with 8 zeros. That dramatic difference in the speed of light and sound is why you often can see things happening in the distance before you hear them, like the lag between seeing lightning and hearing thunder. But those speeds are generally constant for those types of waves. And adjusting the frequencies of those types of waves doesn't change the speed, it just changes the corresponding wavelength. And that ends up affecting human perception pretty strongly. Any questions before we practice a bit of math related to that? All right. So let's do a couple of calculations for both sound and for light using their very different speeds. Speed of sound in room temperature, standard pressure, standard humidity air is 340 meters per second. And we are going to find the wavelength of 2 very different frequencies of sound. 20 hertz versus 10,000 hertz. Now I got the formula here. Wave speed equals frequency times wavelength. And the velocity is the same for both. As long as it's both sound, both moving through air, same velocity for each. What's going to change is we plug in different frequencies and we're going to get out different required wavelengths to construct those frequencies. Different frequencies of sound have different wavelengths, and that is why the different frequencies of sound sound different. What would the wavelength of the 20 hertz be? Thank you very much. The unit on that is meters. 17 meter wavelength. That is a very long wave. It's like a fifth of a football field. Conversely, what's the wavelength of a 10,000 hertz sound wave?
0.6.
Thank you all. And that unit is still meters, and it is very, very tiny. It's like 3.5 centimeters. This contributes a lot to how humans tend to perceive sound. Again, note, changing the frequency doesn't make the wave any faster. Higher frequency isn't going to reach your ear any quicker. It's just going to change the wavelength that is striking your eardrum like a literal drum. some things related to human perception. I chose these two frequencies very specifically for a reason. 20 hertz is the lowest frequency of sound a human ear can, on record, detect. It's the absolute lowest. And frankly, even at that low, in my experience, you're not so much hearing the sound as you are feeling it. These are bass tones when you get the frequency this low. If you've ever been around a speaker that has had the bass cranked up and you kind of feel it in your bones and your teeth more than in your eardrum, this is why. Low frequency has gigantic wavelength, and that means that waves of a frequency this small physically make a lot of air start shaking. It's making a 17-meter long column of air start vibrating, and therefore a 17-meter long column of air is striking you right in your rib cage. And again, in my experience, that's why I feel it more in my bones than my eardrum. Sound any lower than 20 hertz is what we call infrasound. Infra just means lower, so infrasound is sound that is too low for humans to hear. So 0 hertz to 19 hertz is considered infrasound. And infrasound is actually dangerous because smaller frequency, the wavelength of infrasound gets even bigger, and that means there's an even bigger column of air physically striking you in your rib cage. And when air is, the danger there is you can't hear it. You can't hear infrasound. Maybe you can feel it, but you can't consciously hear it. So you don't know it's there until it starts doing stuff to you. Imagine bass tones making your body rattle, but you don't know they're there. Humans exposed to infrasound for too long, literally they can start shaking your organs apart and liquefy your brain. It's not good. Thankfully, infrasound doesn't happen all that much in nature. Things don't tend to naturally make frequencies of sound that low in very high volumes. So you're never in danger of something like this just happening spontaneously. Unfortunately, humans being humans, we've invented sonic cannons that can project unhearable infrasound at people, and it does really messed up things to them if it's exposed to them for long amounts of time. Humans are kind of messed up. But unless that is, you should never encounter infrasound outside of that very specific scenario. Which is good, because again, if it's blasting you, it's adding energy into your body, and you just don't know about it until after it's already hurt you. Related fact though, on a less horrifying note, infrasound doesn't happen a lot in nature naturally, but it does happen in very small doses sometimes. Not a dose that could possibly hurt you, but it's often enough to make you just feel weird. Scientists have gone into haunted houses and noted that there's a higher than average amount of infrasound in them. These decrepit old structures are literally vibrating at a pitch that you can't hear, but is of the frequency in infrasound that can make you feel unwell. It's not enough to kill you, but it's enough to make things start getting weird. And that is possibly responsible for the unease and the haunted sensation that you get in haunted old buildings. Also, possibly unstable cave systems is possibly the advantage this would have had to humans before we had haunted houses. So, infrasound is dangerous, and secretly ghosts might be infrasound. On the opposite end of that is ultrasound. 10,000 hertz is not the highest pitch that humans can hear. This is probably like the highest a speaking voice could get up to if they were really squeaky. The highest that a human can hear is actually 20,000 hertz, which would be an even smaller wavelength. Double the frequency, wavelength gets cut in half. Any higher than that is called ultrasound, and thankfully that's harmless. The wavelength is too tiny to hurt us or to even register, which is good because that's the type of sound that we use in literal ultrasound machines to view babies. And it's also the type of noise that most echolocating animals use for their sonar echolocation. So ultrasound can't hurt you, infrasound can. So big wavelength, bad. Tiny wavelength, harmless. Questions thus far? Okay. We're going to do the same thing with light because light is also a wave, but light's a lot faster, and so the numbers get a lot crazier. The speed of light is 300 million meters per second. It's literally the fastest thing that moves in the universe. I'm just going to abbreviate that to 3 times 10 to the 8th for simplicity's sake. All types of light and all types of electromagnetic radiation in general travel at that speed. And so changing the frequency of the light, again, doesn't change this, it changes the corresponding wavelength. Red light bottoms out at a frequency of 400 terahertz, which is 4 followed by 14 zeros, hertz. Which again, I will just abbreviate as 4E14. Violet light isn't actually that much higher in the grand scheme of things. That's only about 790 terahertz still, so 7.9 times 10 to the 14th. And because they have different frequencies, they too will have different wavelengths. And this affects why we see them as different colors. 3E8 divided by 4E14. Wavelength 1 for red light would be 7.5 times 10 to the negative 7th meters, which is teeny tiny. I can in fact rewrite that as 750 nanometers if I wanted to use a different prefix. And then violet light is 3.8 times 10 to the negative 7 meters, which you could also write as 380 nanometers. The wavelengths of light are incredibly teeny tiny, and their frequencies are huge. High frequency means that a ton of these waves are entering your eyeball every second, literally millions, trillions of them. But they are so very small. And the different frequencies and wavelengths of light just trigger different photoreceptive cells in your eyeballs, and that's how you register them as different colors. Questions? All right. Interesting fact, in my opinion, while I've got these wavelengths up on the board, this is not the smallest thing in the universe. There are things smaller, like atoms, namely. But if you build a microscope, an electron microscope, that is designed to view things smaller than this, color kind of stops existing. Because if you are shrunk down to something smaller than the wavelengths of light, you can't really see the light anymore. It becomes kind of undifferentiatable. So technically, when Ant-Man gets too small, everything should either go grayscale or he just shouldn't be able to see. Questions? Okay. Now, once again, wave speed is constant for a given type of wave in a specific medium. If you want to change the speed of a wave, you have to change the medium that the wave is traveling through. If you want sound to reach you faster, you got to stick your head underwater. Now, because the speed of the wave won't change based on your own motion, something weird happens if you start moving while making sound waves. Or really any type of wave, technically. Say you are screaming and producing 500 hertz sound, and then you start running, maybe at 30 meters per second. You're pretty quick. You don't add your speed to the speed of the sound. It's not quite like you're running and then you throw something and then your speed gets added to the speed you threw the football at. So running doesn't make the sound any faster. You can't add the speed that you are running at to the speed of sound. The running doesn't really get the sound any closer to its target. But something differently weird happens instead because the wave speed can't change. This is a phenomenon called the Doppler effect, which you might have heard that word before in reference to something like Doppler weather radar. And that is ultimately the effect I'm describing. As an example, let's say that you, the observer, are standing still, and some distance away is an ambulance that is also parked stationary. So right now nothing is moving. And that ambulance turns on its siren, starts blasting 500 hertz sound, which is pretty low. If everything's standing still and it's making 500 hertz sound waves, you're going to hear 500 hertz sound waves. Nothing weird isn't happening yet. But something weird starts happening once the ambulance begins moving. Once the ambulance starts moving towards you, now the ambulance isn't going to catch up to the sound wave it just made. Sound is very fast. You'd only catch up to it if you were moving Mach 1 or higher, which I've never seen an ambulance do. But if the ambulance is driving towards you, it's at least getting closer to the wave it just made than it's supposed to be. Like if the wave is supposed to have a wavelength of 1, a new wave is supposed to come out every 1 meter. But if the ambulance is moving towards the wave it just made, the next wave comes out closer to the last one than it's supposed to. Kind of like moving one end of a slinky closer to the other end. The coils get closer together than they were. So if this is supposed to be the wavelength, and the source at the other end draws nearer the wave head than it's supposed to be, that kind of shrinks the wavelength, because the next one comes out before it's supposed to, or closer than it's supposed to be, and that kind of shrinks the wavelength. It literally scrunches the waves up like the coils of this spring. And when you decrease wavelength, you increase the perceived frequency. The speed doesn't change again, but changing the wavelength will change the frequency. So when the ambulance approaches you, you actually hear a higher pitch than you're supposed to. Conversely, once the ambulance passes you and is driving away, the reverse happens, because now it's getting further away from the sound wave it just made, and that stretches the wavelength outward. Bigger wavelength, smaller frequency. So the pitch drops when the ambulance drives away from you. To use very advanced scientific jargon, this is the reason for the meow that you hear when something passes you. Again, very academic term here. The higher pitch on the approach is the meow, and the lower pitch as it moves past and away from you is the meow. Sound good? Do I sound ridiculous? Better question. But that thing that you've heard anytime any vehicle passes you is a real thing. We have a name and math for it. Speaking of math, this is the formula that one would use in this scenario. The way that it works is you take the frequency that the device is supposed to make. That would be the frequency of the original source of the wave. And then you multiply it by this very strange looking fraction that adjusts that frequency based on the speed things are moving at. Fraction consists of, in the numerator, wave speed plus observer speed. You would be the observer. You are the thing with ears listening to the sound wave. The underside of the fraction is wave speed minus source speed. The source of the wave is the thing making it, which in this example would be the ambulance's siren. So the speed of the ambulance. Wave speed would be the same number because it would be sound for both, and that doesn't change. So if we're looking at sound waves, you plug in 340 for both of these, and then these numbers would change based on which is moving, you or the ambulance. And the point of this very big fraction is just to multiply it by f source to make it either bigger or smaller, and that'll tell you the adjusted frequency that you actually end up observing. So f observed is the final frequency that you, the observer, get after this fraction changes the source frequency. Conceptually, how's that sound? Pun not quite intended. All right, to prove that this works, I'm going to run through a sample calculation for the ambulance situation I just described. Formula's right here. We have the ambulance. It's making 500 hertz sound, and that is what you correctly hear when nothing is moving. If nothing's moving, both V observer and V source are 0. Therefore, the fraction would be wave speed over wave speed, 340 over 340. Fraction is 1 times f source. You will hear the normal unaltered wave if nothing's moving. Once the ambulance starts moving at 15 meters per second towards you, then things start changing. So over here, we're going to do the frequency on the approach. F observed 1. I'm just going to say obs instead of observed. The source frequency is the 500 hertz. That is the original noise that the siren is supposed to make. Top part of the fraction is wave speed, 340 for the speed of sound, plus your speed. If you're standing still, that is 0. On the underside of the fraction, wave speed is still 340, but now we're going to subtract out the speed of the ambulance. Technically, we are plugging in a positive V source because the ambulance is getting closer to us, but the fraction, the formula, has a negative in it already. So you plug in positive if the object is drawing towards you, and the negative of the formula takes care of itself. And so this fraction is going to adjust the original source 500 hertz. Questions before I simplify the fraction? All right. 500 times, the numerator is just going to be 340 plus 0, doesn't change anything. The denominator, we've got 340 minus 15, so that's going to shrink the denominator down to 325. Note, that fraction is going to solve to a number that is greater than 1. We have a bigger numerator than denominator. So this fraction would be like 1.05, And that's why multiplying it by the source frequency is going to give us a higher frequency, observed frequency, when the ambulance drives closer to us. I believe that comes out to 527. Nope, 523. So just by virtue of the ambulance driving towards you, you are hearing a higher pitched sound than you're supposed to. And that difference of about 23 hertz is enough for the human ear to notice. You would notice the difference. Sound good for the first part? All right. The inverse happens when the ambulance drives away. Even if it's still moving at 15 meters per second, the main difference in the math is going to be we have to plug in a negative 15 velocity for the ambulance if it is moving further away from us. So F obs 2. Siren is still trying to blare 500 hertz sound. Speed of sound is still 340. We are still not moving. The only difference is we plug in negative 15, and the negative that's inherent to the formula is then going to change a few things. This time around, we get 340 over 355. That fraction is going to be smaller than 1. And that is why it's going to multiply into the 500 to create a smaller frequency. Not a whole lot smaller, but enough for the human ear to be able to notice. I think it's 479. Yes. So now it'll drop by about 21 hertz. Which is at minimum, it's got to be at minimum like a note, musically speaking. So again, ambulance driving towards you, higher frequency. Ambulance driving away from you, lower frequency. This is the and this is the yow. Sound good? Pun intended that time. All right. Couple of quirks related to this formula. One, I don't want to hold this up on the weekend, so I won't run through the whole calculation, but I'll just point out in relation to this blurb. You could get a similar effect if the ambulance was still parked and you were the one moving. In that case, hypothetically, you don't have to erase anything, I'm just demonstrating. If you were running towards the ambulance is parked and you're moving, you get the same basic effect. If you're running towards it, the fraction would be bigger than 1, you get a higher frequency. If you're running away from it, you plug in negative 15, you get a fraction smaller than 1, you'd hear a lower pitch because of that too. So you can technically do this without a car. You can do it while running with your own legs. The only question is whether or not it's going to be noticeable based on how fast you can move. But I have tried it. You can set up a speaker in the middle of like a football field, run full tilt towards and past it, and I've noticed very slightly the meow just from me running. It's amplified the faster you're moving, so it's not super obvious, and it's very easy to be distracted by just the running. I have a hard time listening if I'm moving. But you can do it if you want to try it out. That means that the flash going from 0 to 600 super quickly would probably get some really weird tonal whiplash. Why is this important? This is important because basically every form of speed detection technology used by man or dolphin utilizes this principle. If you've ever heard Doppler weather radar, we call it that because it uses the Doppler effect, and it's the same with speed radar guns. Basically, the device blasts radio waves at something, it knows what frequency of radio waves it is creating. Radio waves bounce off of the target at a different adjusted frequency based on the velocity of whatever it hit, and then the machine is physically listening for whatever different frequency it gets back. And based on those two frequencies, it can calculate the speed of whatever the radio wave bounced off of. Doppler weather radar does that by shooting radio waves at clouds to determine how quickly they're moving, figure out where they will be in the next hour, and who's getting the rain. But again, normal speed radar detectors do this too. You just shoot it at a car instead. Bats and dolphins and anything capable of echolocation does the same thing, just with sound instead of radio waves. And they do all this math in their heads. Bats are pretty smart, which I feel explains Batman a little bit better. And if you like space, astronomers use this too to determine if a star is moving towards us or away from us. If it's moving closer to us, frequency drops, and therefore it red shifts. If it's moving away from us, frequency increases, therefore it blue shifts. So if you've heard those terms in conjunction with space, that's what they mean. How do you feel? All right. That'll cover it for today. Next week, we will talk about various wave types, go over the specifics of how sound waves function. But before that, we'll cover that Wednesday and Friday. Monday is Eclipse Day, which I'm excited for. And again, you should grab Eclipse glasses before you go. You're welcome to a second pair if you want a second pair. Let me know if you have any questions or need anything over the weekend. And please have a wonderful day and weekend.
Have a good one.
You too.